All right. Hi, everybody. Hope you're all doing well. Jason's going to start this with his section and then I'll get onto mine. If you have any comments that you want to make, you can obviously feel free to unmute yourself, or you could drop it in the chat. I'm checking that out too. You could post it publicly or privately DM me. Do you guys have any questions before we start? Okay, go for it.
Okay, so first let's do a general overview of the cell cycle. So we have a couple different phases. G1, we'll go into a little more detail later, but we'll just run through it really quickly so far. So really quickly first. G1 is the start of the cell cycle. So G stands for gap phase, or also growth phase, depending on which textbook you're looking at. G1 is when the cell prepares for DNA replication. When it's doing this, it has to make sure that there is enough nutrients in cell machinery and no mutations in the DNA. Once it goes through G1, it commits to the cell cycle. So it's called like the point of no return. We'll go through that later. It is that's when and the point of no return is when it goes through the restriction point. Oh, actually, I skipped G0, but G0 is the non-dividing state. So that's for example, a cell that's like a neuron or like a red blood cell Laura mentioned that's like doesn't need to divide. That'll be in G0. So it's a fully differentiated cell. After G1, you go to S phase. S phase stands for synthesis phase. That's where the DNA replication occurs. We'll go into that more next week. And there is a checkpoint in S phase 2. After S phase, we go into G2. That's a second gap or growth phase. That's when the cell prepares for chromosome segregation, and there's a checkpoint here too. And then finally, we have M phase, and that's where you have your typical prophase, metaphase, anaphase, telophase. Again, we'll go over that more next week. And you also have a metaphase checkpoint. So throughout the cell cycle, we have these things called cyclin-dependent kinases, which are super important. Cyclin-dependent kinases are the master cell cycle regulators. They're serine-threonine kinases, and you need to activate them for processes in the cell to occur. So they get activated when cyclin binds to the CDK. It exposes the active site of the CDK, so it can then phosphorylate other things. CDKs are regulated by cyclin levels. They can also be regulated by phosphorylation or dephosphorylation, or you could have CDKIs, which are CDK inhibitors. For a CDK to be completely active, you need phosphorylation and cyclin. And when you reach a checkpoint, the cell breaks, puts the brakes on the cell cycle by inhibiting or deactivating CDK. So usually with CDKI, or it'll just destroy the CDK. So like I said, cyclins are required for CDK activity. Cyclins like I said, they activate CDK's kinase activity by exposing the active site when it binds. There's a really good movie in the second video, I think it was this week, that Laura highlighted. And what cyclins do is they basically like tell CDKs what to phosphorylate. Cyclins are regulated by two things. So the only way you can regulate cyclin, pretty much Laura mentioned today, was either by making more of them or destroying them. So you can make more or less of them. So you can make more or less of them by regulating transcription and translation at specific points, or you could destroy cyclins by ubiquitin-mediated proteolysis. We talked about that a little bit during the first exam, but that's pretty much just tagging a cell with ubiquitin, and when it's tagged with ubiquitin, it's destined to go to the proteasome for destruction. Okay, so a little more detail of the G1 phase. So like I said, cells in the G0 phase are in the non-dividing phase. but to get out of the G0 phase, they need to receive a growth factor signal. The growth factor signal is part of like the RAS MAPK pathway that we talked about last week or 2 weeks ago. Once they get that signal, they can enter G1. So G1 is the entry point for the cell cycle, and this is where cells grow and prep for DNA replication. But before they do that, they have to check for certain things. So they must receive the growth factor signal. They must check for DNA damage. They check for early G1 cyclin, which is cyclin D, as you can see in this diagram. They check for that the cell's the right size and that it has the right nutrients and energy, and they make sure the pre-replication complex is formed. So the restriction point, or start is what it's called in yeast, is the point of no return. So once it enters this, it can't get out of the cell cycle unless it is pretty much destroyed. Yeah. So the next phase is S phase. This is where genomic DNA is replicated. So if there is a problem with DNA replication, then if the cell senses a problem with the DNA, then it can temporarily halt DNA replication here in the S phase checkpoint. Laura mentioned that the S phase, like not everybody like recognizes an S phase checkpoint, but Laura does. So just know that cells can temporarily halt DNA replication. We'll talk more about the mechanism of DNA replication next week in the cell cycle 2 section. After S phase, we go to G2 phase. So in the G2 phase, cells, they go to G2 phase when they're done replicating their genomic DNA. So once the genomic DNA is fully replicated, they check that it's replicated correctly and completely, and if there is any damage. If it's not, it gets stopped at the G2 checkpoint, which inhibits entry to M phase until everything is right. So a cell could get stuck at G2 checkpoint if there is DNA damage. Finally, we go to M phase. So M phase is where spindle assembly and chromosome segregation happens. The checkpoint for M phase is the spindle assembly checkpoint. What the spindle assembly checkpoint does is inhibits anaphase. Anaphase, which we'll talk about next week, is chromosome segregation. So it'll inhibit chromosome segregation until the chromosomes have proper microtubule attachment. So microtubule are going to be important for next week. So make sure you are confident with all your microtubule stuff. So once the cell finishes and passes the checkpoint, it undergoes cytokinesis, which is just like the splitting of the cell into two. So any questions on cell cycle stuff? This is just a general overview. We haven't talked about any mechanisms yet this week. Okay, like I mentioned, there's checkpoints throughout the cell cycle where the molecular breaks, in quotes, can be put on the cell cycle to basically fix any problems that are happening. So in G1, it checks for damaged DNA, or if the cell's like in a toxic environment, you wouldn't want to replicate, or you wouldn't want to spend your energy replicating, because replication is a costly process. So you'd want to focus on surviving in the environment. S phase, the cell checks for damaged or incompletely replicated DNA, because that's when DNA is synthesized. In G2, you're checking for damaged or incompletely replicated DNA. Pretty much the same thing, but just double checking again. You really want to make sure our DNA is replicated correctly, because if it's not, it causes a whole host of problems. And M phase checkpoint is when chromosomes are checked, whether chromosomes are properly attached to the mitotic spindle. So the way like I mentioned, the way you activate these molecular breaks is through targeting CDK. So you'd either upregulate production of CDKIs, or you'd activate them with certain cyclins or something. if the issue can't be fixed, then the cell pretty much just kills itself. So it'll go through programmed cell death or apoptosis. You wouldn't want to replicate a damaged cell because that can cause more problems. Any questions so far? Great. So what happens if you find a DNA mutation in G1? The protein that gets activated is p53. p53 is a transcription factor and tumor suppressor that is super important for DNA damage response. So p53 activates another protein called p21, which is a CDKI. So what it does, it'll inhibit the CDK at that part of the cell cycle and put a brake on it. If the p53 senses that the DNA damage is irreversible, it'll signal for apoptosis. And yeah, so you wouldn't want this happening if everything is okay. So if p53 isn't needed, it's degraded, and it's a very heavily regulated process. Any questions? Otherwise, Sebastian's going to take over.
Or is that at the end?
That's at the end.
Okay. All right. God, what was I talking about? Oh yeah. So what Jason was saying, CDKs are the master regulators, but what that means, like in a little bit closer detail, obviously in every step of the cell cycle while the cell is dividing, there's a bunch of different proteins that need to be turned on, turned off. So to turn on or turn off those proteins, CDK is responsible for doing that. So that's why we call CDK like the master regulator, because it's responsible for activating all the proteins that you need to successfully complete whatever phase of the cell it's in. Obviously, that's super important. That's why it's very regulated. CDK is regulated in 3 different ways. Jason touched about this a little bit. One of them is the concentration of cyclin. Another way is phosphorylating or dephosphorylating it. And the last way is for CDKIs or inhibitors to inhibit CDKs. What was he talking about? Oh yeah, okay, so just a little bit more. CDK can't work as a kinase. It can't phosphorylate or dephosphorylate anything unless it's bound to a cyclin. And what cyclin does is it gives CDK the ability to phosphorylate the proteins relevant for that cell cycle. And what I mean by that is, so CDK alone can't do anything. It's useless. But when CDK is bound to cyclin B, for instance, CDK and cyclin B together can start phosphorylating or dephosphorylating all of the proteins relevant in the M phase. However, if CDK is bound to cyclin B, CDK and cyclin B can't do anything in the G2 phase. It can't do anything in the S phase. So depending on what cyclin CDK is bound to is what cyclin will be regulating in that particular phase. So do you have any questions about that? Okay, so cyclins, like I said, they just help CDKs do their thing. The only real way to regulate cyclins is by their concentration. So by producing or destroying cyclins, there's no other like mechanism for that. You need to, yeah, okay. So this kind of just like reiterates everything that I was saying before. The cyclin during the M phase, which is, let's see, okay, cyclin B looks like it's very relevant during the M phase. If CDK needs to phosphorylate or dephosphorylate things throughout the cell cycle, it needs to be bound to a specific cyclin. So that's why over here on this graph, you see that that's the reason why you get all of these fluctuating concentrations for different cyclin, because when you're in G1, the cell or CDK is really going to need cyclin bound to cyclin E, CDK bound to cyclin E. During the A phase, I'm sorry, S to G2 phase, you need cyclin A because cyclin A plus the CDK will be responsible for phosphorylating all of the proteins responsible in these 2 phases and so forth. Okay, so I have a question for you. Let's say that why couldn't all of the cyclins be produced at the same time for the entire duration of the cell cycle at the same concentration? So for instance, why isn't cyclin D, E, A, B just not all made all at once and last for the entire cell cycle? What ideas or what problems do you guys see with this situation?
because the different cyclin are used for specific purposes throughout the cell cycle. So if you make them all at once, then I'm assuming the cell cycle won't work properly. Just guess.
Yeah, exactly. CDK, yeah, that's exactly right, Keshwar. CDK needs to be bound to the appropriate cyclin during the appropriate cell phase. If you have, yeah, if you have every single cyclin produced all at equal concentrations throughout the entire duration of the cell cycle, CDK is going to get a bunch of mixed signals. It's going to, there's, first of all, going to be a lot of cyclin traffic going around. There's going to be a bunch of cyclins bumping into each other and just diffusing everywhere. So CDK is going to probably bind to the wrong cyclin, and it's not going to be able to phosphorylate or dephosphorylate whatever proteins it needs to in that particular phase, because since all cyclin concentrations are at equal concentrations, it will most likely bind to the wrong cyclin at the wrong time. So does that make sense? That's why you have these fluctuating cyclin concentrations. Okay. Okay, so you didn't take that off. So a little bit more about the cyclin and the CDK complex, sorry. So I mentioned before that CDK alone can't do anything. So CDK alone has this thing called an activation loop, which is also called a T loop. The activation loop in CDK is what's responsible for phosphorylating and dephosphorylating all the proteins. However, CDK alone, like I said, is inactive. It's inactive because the activation loop, the loop that does all of the phosphorylating and dephosphorylating, is tucked away inside the CDK. So that's why CDK alone is considered inactive, because its activation loop is just tucked inside and it can't access any proteins. However, when CDK is bound to cyclin, when those two come together, the CDK undergoes a conformational change. So it changes shape. It changes shape so that the activation loop is now exposed. Yeah, so now that the activation loop is exposed, now it can contact the proteins necessary for that particular cell cycle phase. However, just CDK bound to cyclin alone doesn't cut it yet. So even when these two are bound together, yes, your activation loop is exposed and ready to phosphorylate and dephosphorylate other proteins. It's still technically not active. To make it officially active, you need to activate the activation loop with something called the CDK activating kinase. So it pretty much just adds a phosphate group to the activation loop, and it allows the activation loop to then be able to phosphorylate or dephosphorylate whatever proteins it needs to during that particular cell cycle phase. However, another thing that could bind to the CDK cyclin complex is, instead of the CDK activating kinase, it could be attacked by CDKI, which is an inhibitor. And the CDKI, it either prevents the CDK from being phosphorylated, or prevents CDK from binding to its substrate. I don't know how relevant that is, but just so you know, just different ways that CDKI can inhibit CDK's activity. Any questions about that? Okay, so here's just another little cartoon about everything that I just said. CDK alone can't do anything, but when CDK is bound to a cyclin, it's going to be able to target and phosphorylate target proteins that are particular to that cell cycle phase. So this cyclin that it's bound to can only activate proteins relevant in the S phase. So whatever proteins are necessary for DNA synthesis or replication, like the helicase or whatever. Okay, I have another problem for you. So here's a few things: CDK alone, cyclin alone, the complex. Which one of these options would you say is most appropriate for CDK alone? You could drop it in the chat. I don't have a poll feature, unfortunately. You could drop it in the chat, or feel free to turn on your mic. So which one of these options is most, best appropriately fits the CDK alone? I know it's sour. Actually, I don't know the answer, so let me think about this. I'll race you. I'll race you to get the answer. What is it? Give me to find it, please. Okay. Okay. Yeah, I'm seeing some choices for D. I'd agree with you. It is D. CDK is the kinase that does all the things. Obviously, CDK is not alone. I mean, it's not activated yet because it is alone. But when it's not alone, then it'll be able to activate whatever. It'll be able to function as a kinase, uh, as usual. What about cyclin alone? Any guesses? What is it again? Okay, yeah, this one is a little trickier. Cyclin alone, so cyclin actually doesn't phosphorylate anything. It's not a kinase. CDK does phosphorylate things. However, it needs to be in the complex before it can phosphorylate anything. Cyclin by itself doesn't phosphorylate anything, but it allows for CDK to phosphorylate target proteins. So cyclin alone, someone mentioned E. I would agree with you. Cyclin alone, remember, you need the appropriate cyclin at the appropriate concentration at the appropriate time. So the timing of the production as well as the timing of the destruction, because remember, if you don't destroy your cyclin in time, we'll run into that situation from the previous problem. If you have too much cyclin floating around everywhere, it's going to be a disaster for the cell. So cyclin alone needs to be degraded if it's just hanging out there and it doesn't have a purpose anymore. So I would agree with E. How about 3? The cyclin CDK complex. I kind of just mentioned one already, but I missed my poll function. Do you guys have any guesses? Okay. Yeah. Okay. So seeing a pretty unanimous vote for A, I would agree with you. The CDK cyclin complex does phosphorylate target proteins. Thank you, Jessica, for reminding us. Yes, it does have to be phosphorylated. So the CDK cyclin complex has to be activated by the CDK activating protein before it can be technically active. So before it could start phosphorylating its targets, it does need the activating protein. So thank you for that clarification. Is there another option that you guys can think of? There, like, do you see another potential answer for this one? Another acceptable answer, according to Laura, would be E, because remember, um, your CDK cyclin complex is only responsible or can only be responsible for phosphorylating or dephosphorylating proteins to that particular cell cycle phase that it's in. So CDK bound to cyclin E, whatever, is responsible for the G1 phase. However, after the G1 phase is over and you're moving into like G2 or M, whatever, you no longer have a purpose for that cyclin CDK bound to cyclin E complex, right? So it can also be, I'd argue that another acceptable answer would be E, because you also need to degrade this complex once it's no longer relevant for that particular cell phase. Are CDKIs a totally different type of protein? I think so.
Yeah, I think so. I mean, they would completely different function. So they have to be a slightly different type of protein. So CDKIs will inhibit the CDK.
Yeah. Can 2 also be C?
I don't know if cyclin itself triggers destruction of cyclin.
Yeah. There's different proteins responsible for the detection of cyclin concentrations. So when the cell detects that there's too much cyclin B and we're moving on from this particular phase, it will, yeah, it will well, no, actually no. So the cyclin doesn't like implode on itself, but there are regulatory proteins that are responsible for sequestering that cyclin that's no longer relevant to the proteasome to be annihilated. So cyclin alone doesn't destroy itself, and it doesn't detect itself for being in too much concentration. There are actually other proteins that will do that, that will detect that there's too much cyclin, and it will destroy it for you, but it doesn't do that alone. Okay, so any questions about that? Okay.
Great. So which of the following ways are ways in which cyclin levels are regulated in the cell cycle? We've talked about a couple of these, but what do you think? Yep. So one person said AB, one person said D, which is pretty much the same thing. So yeah. So the answer is two of the above are true, and the two that are true are transcription and translation and ubiquitin-mediated proteolysis. So the key concept here is that cyclins can only be regulated by making more or less of them. They're not like inactivated. So their cyclins themselves are not phosphorylated or dephosphorylated. That's a key idea. So yeah. Okay, last question. Or we might have one more. I forget. Which of the following statements correctly describes P53? Oh, we do have one more. Okay. I'm seeing 1C. Any other guesses? Great. C, because P53 will lead to P21. Yes. So like Jessica said, activation of P53 leads to inhibition of the cyclin CDK complex by a CDKI, which, like Jessica said, is P21. Any questions on those two problems? Great. So last question, and then we can get out of here. So use the following choices to fill in the blanks. The commitment point for entering the cell cycle is called start in yeast and R in vertebrates because restriction point. The molecular mechanism at this point in the cell cycle involves something being produced, which binds to something, which then becomes something. I think cycle to produce first. The answer is C. Okay. Yes, everyone's saying CDA, which is exactly right. So G1 cyclins are produced, and which bind to the appropriate CDKs. And then once they cyclin and CDK bind, they become activated. So not too bad. So this is the first 3 videos of the week. Friday's review session will cover the review of the stuff briefly and the stuff from the fourth video. And then next week, which the fourth video definitely has more mechanism stuff. So I would definitely recommend checking out the Friday review session. And then next week has a ton of mechanisms. So get ready for that. Yeah, any questions? Otherwise, that's all we have.
Right. Thank you, people.
Thank you.
All right, have a good night.